All right, knuckleheads, let's talk statistics. I'm hoping that some of you have had a little bit of introduction to statistics in math class before. And that's all that today is going to be, is just an intro. I want you to understand, though, that standard deviation and standard error of the mean will be on the AP biology exam. The full-on formulas will be on your formula sheet, and it will absolutely be on the exam. Today is just an intro to statistics. I'm going to kind of simplify things. We'll go into it in a lot more depth later on, so no, getting panicked or, whatever. So at this point in the lab, you should have already recorded all the data from your reader. So your reader should have done 3 trials for all the different through A through test D2. And you should have determined whether they were incongruent or congruent data. Okay. So now in your lab, you have some definitions that kind of tell you the difference between standard deviation and standard error of the mean. At this point, I'm going to use those terms a little bit interchangeably. They are not the same and they are not used the same. But for where we are, I don't care whether you're saying standard error or whether you're saying standard deviation. So what I hope to accomplish, I'm going to see if I can, nope, that's not what I hope to accomplish. What I hope to accomplish in this video is to show you how to draw the bell curve, and some of you may have done this before. Awesome. And then I want to show you how to use error bars. And then I'll have another video for those of you that are a little less sure about your math, showing you how to calculate the standard deviation and standard error on the second, let's see if I can pull it up there, the second data table. You need to calculate those, and I will put a video up just showing myself doing some example data, and then you can take a look at it. Okay, so what we want to take a look at is this bar graph. I'm sorry, well, it's sort of a bar graph, but it's a bell curve of normal distribution of data. Now, not all data has normal distribution, but we're talking about data that does have a normal distribution. And I'm going to give you an example of data that's normal. This is a super classic example, human height. So we have, with data about how tall people are, the vast majority of people are an average height. That's where the name average comes from. So we got the largest number of people are an average height. And then as we go out, we have fewer and fewer people that are either taller or shorter than the average. So that's where this bar graph comes in. I'm sorry, the bell curve. Why do I keep saying bar graph? Because it kind of looks like a bar graph. That's why. So that's where this bell curve comes in. Now, mathematicians and scientists got together and they did a little math and they agreed with each other. The numbers are arbitrary, which simply means that mathematicians and scientists agreed that we'll use these numbers to indicate whether something is statistically significant or not. The numbers could be different, but mathematicians and scientists said, we're going to use these numbers. Okay, so just put that in the back of your mind for the moment. These are the numbers. We're always in AP biology and honors chemistry. We're always going to use these numbers. Your stats class, these are the numbers you're going to use. Okay, so let's pretend that this bell curve is a graph of human height. And the tallest part of the bell curve is the number of people that are average height. And I don't care whether we're talking men or women. We're just talking about average height. Okay, and then as we go out from average height, to the right might be the taller people, and to the left might be the shorter people. So when we go to 1 minus 1 standard deviation, oops, I'm not using give me a second to get my pen on. There we go. Okay, if we were to look at the minus 1 standard deviation, everybody from here to here, that is, they're shorter than the average. And that makes up about 34% of the population. Likewise, everybody from here to here, which is plus 1 standard deviation, this arbitrary number that scientists and mathematicians agreed to, make up another 34% of the population. So roughly 68% of the population, that's this right here, roughly 68% of the population falls a little bit below average or a little bit above average. I'll keep going with that. I've got another idea to explain, but let me just keep going with that. So then we start getting people who are actually unusually tall or unusually small. They might fall in this category way over here. They are 2. It's actually a minus 2 standard deviation, or a plus 2 if they're very tall, a plus 2 standard deviations from the normal. So they're significantly, in this case, significantly taller than usual. In our lab, instead of SD, which stands for standard deviation, we're going to do SE, which stands for standard error. And then there's going to be a little subscript that's the letter X. And yes, it looks like the word sex. Don't say sex. Say SE sub X. That's how you say it. Or standard error of the mean. So that's what, instead of SD, we're going to do SE sub X. You can do both. It doesn't matter. But in my stuff, you're going to do SE sub X. Okay. So 95% of people fall within this range of being tall or short, that far away from being normal. But what if we had a person who was 8 feet 5 inches tall? That person is going to be out here, well beyond the third standard deviation. So scientists have agreed that anything, I'm going to switch colors here. Actually, I should back up a few. I'm going to clean it up a little bit. There we go. Scientists have agreed that anything that falls within, let's switch colors, anything that falls within the 95th percentile, the 95% of people or 95% of data points, anything that falls in there, that's normal. It's boring, it's not interesting, nothing exciting's happening, there's no unusual discovery. However, scientists and mathematicians have said anything that falls beyond the second, the plus or minus SE sub X, anything that falls in the 5% above or the 5% below, the 95th percent above or 95th percent below, that's a funny way of saying it, that's actually statistically significant. So these guys, wowza, who are they? What are these data points? Cool beans, amazing discovery. So anybody who is beyond -2 or +2 SE sub X, who's beyond those are the folks that we're going to take a look at. So I've got somebody pretending who's 8 feet 5 inches tall. Holy cow, that's a really tall person. I don't even remember who the tallest person is or how tall they are. I don't care. 8 feet 5 inches tall. Right away, I know that they are beyond my my +2 standard or standard error of the mean. I know that they're beyond that. So they're statistically significant to me. The first thing that I wonder when I look at that person, when I read that that person is 8 feet 5 inches tall, is whether there was a measuring error. I was going to say 99% of the time. I'm throwing out a statistic that's not real. Most of the time, when we have like this crazy statistic, most of the time it's because we screwed up our math or we screwed up our measuring. So the first thing I'm going to do with that person who's 8 feet 5 inches tall is insist that somebody measures them again. And several other people measure that person again so that we can confirm they really are that tall. Then, wowza, that person is 8 feet 5 inches tall. They need to be studied. We need to find out, does that person have a pituitary tumor? The pituitary gland is what makes your human growth hormone. Do they have too much human growth hormone? Do they have an unusual mutation in their DNA? What's making that person so remarkably tall? And we're going to try to get more information about that person. And likewise, if we saw somebody who was a very small person, a little person, we might want to look at them and look at their genetics and find out about their human growth hormone. Okay, so now for our lab, for the purposes of our lab, what we're going to look for, and I'm going to help you graph this, what we're going to look for is any of your readers that scored beyond 2 plus or minus 2 standard errors of the mean. It's so awkward. I'm just going to say standard deviations. That if they scored plus or minus 2 standard deviations beyond the mean in that case, and we're going to say, hey, why did that person score so high or so low in that circumstance? Now, I have to give a really truthful aside. The Stroop effect, which is what you guys are studying, was sort of made up in the 1930s, and whether it is a significant measurement of anything is debatable, but it's fun for us to take a look at it. So the idea with the Stroop effect is that it is supposed to measure a person's ability to focus even when there's all kinds of dissonant cognitive stimuli, all kinds of other crazy things going on, that person can still focus. So you should be hypothesizing right now who might score way way on one end or way on the other end. And one of the hypotheses you might have is maybe people with attention deficit disorder, maybe somebody who doesn't focus well on stimuli might score really high or really low. Well, I'm going to tell you, I don't believe that for a second. I'm going to guess that all of you guys who are ADHD are going to score within the plus or minus 2 standard deviations. If you don't, I would check your math. That would be the first place I go. I would guess that your math is funky. So anyway, does it mean anything? No. The other hypothesis that could cause somebody to score, I just spit everybody, could cause somebody to score perhaps really low on the Stroop Effect, the score of the Stroop Effect, is a traumatic brain. Now, that could be a brain injury, so they actually have a physical injury to the brain, or they could be psychological trauma. So somebody who's really stressed out right now, somebody who's been experiencing psychological problems, like stressors, that could affect their ability to focus, and that could affect the Stroop score. However, please don't read anything into the meaning of this data, because whether the data is significant or not has been debated for decades now. So we're not going to try to pretend that we can tell anything meaningful from this. So we're going to take a look at it. We're going to see if your reader scores two or more standard deviations from the norm. And we're just going to do the statistics on that. Now, the last thing that I wanted to talk about in this set of notes, you're going to, let's see if I can show you here. I'm going to jump back. It doesn't always work perfectly. So here's where you're going to calculate that standard deviation and standard error. You're going to have space to do all your work, and I'll show you that on the next video. And then the very last page says, now add 95% confidence intervals, which we just say error bars, to figure 1 on page 2. So you should have already done figure 1. You should have already made your graph. Give me a second to get there. Blah, 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 blah. Don't fall asleep while I'm drawing. Here we go. This is your bar graph that you should have done. Please make sure that you have a meaningful title and that you've labeled your axes. That is just such a gimme and such an easy way for me to take off points. Don't fall for that one, okay? Don't be that person. All right, so you should have a bar graph right now. Now what we're going to try to do is, once you've calculated your standard error of the mean, and the plus or minus 2 standard error of the mean, once you've calculated that, then we're going to draw error bars on this graph. And I'm going to show you what error bars are. Some of you, this might be familiar. Okay, now I forget. I think I have to use 2 fingers. There we go. All right, here's a bar graph that I pulled off the internet. And the black lines, these things that you see here, those are called error bars. And the error bars are not arbitrary at all. Those are real statistics. Notice that this error bar is bigger than this error bar, which is much smaller than this error bar here. Where the error bars are placed is super important. So in the math, they calculated in this particular graph. So now this graph sucks because it's missing a title and it's missing labels. And that's fine for our purposes, but just be aware that we have no idea what this graph is about. Okay, so in their calculations, they determined that this was their mean. But then they calculated 2 standard error deviations above and 2 below. And that's this number here and this number here. They plotted those 2 points. One is always above, for example, the taller people, and one is always below, for example, the shorter people. And what that means is, listen carefully, everything in this area here is normal. So the mean, let's see if I can say that another way. Not only is it normal, but the mean could be anywhere from here to here. Anything, this bar graph, if I did this experiment again, whatever this experiment is, if I did this experiment again and again and again and again and again, one time I might get the mean to be here, another time I might get the mean to be here, another time the mean might be here. So the bar might get a little bit higher or a little bit lower. Just like when you're flipping the coins, 10 times you might flip it 5 out of 5, but once in a while you might flip it 8 heads 8 times. So that one might be a higher average than usual. So these bars tell you for a 95% confidence, gosh, this is getting awkward to talk to you about. Within those black bars, within the error bars, we have 95% confidence that the average data point is somewhere in there. The more we do this experiment, the shorter and shorter the error bars get. So maybe I didn't do this experiment very many times, but maybe I did this experiment more times. So that's why some error bars are really big and some error bars are really small. So if they're really small, it means you can be really, really, really confident that this right here is the mean, and that you're not going to have a random mean up here and you're not going to have a random mean down here. You can be pretty confident that the mean is somewhere in that little gap there. But let's use an eraser this time. With this one, there we go. With this one, we have a huge error bar. It's enormous. And so the mean could be here one time. There we go. The mean could be here one time. It could be down here one time. It could be all over the place. So we have much less confidence in that particular error bar. Now, there's one more thing you have to understand about these error bars, and it's super fun and guaranteed. Every AP biology test I've ever seen requires that you be able to do this. So now we're going to look at the error bars and we're going to compare them to each other. So let's compare these two bars. Let's compare these two bars to each other right here. So there we go. We're going to compare these two bars to each other. This giant error bar here says the mean could be anywhere in this space here. And this giant error bar says the mean could be anywhere in this space here. These two error bars overlap. And so what that tells us is that although the two bars look like they're different heights, that might just be a coincidence. It might not be statistically significant. I can flip a coin 10 times and get heads 8 out of 10 times. Is that statistically significant, or is that normal variation? So for these two bars, we're saying because their error bars are so huge and they overlap with each other, we're saying there's no difference. There's no statistical difference between those two error bars. Now, let's change this. I'm going to go make sure, let's see, I'll use an eraser. Make that go away, this go away. Now, what if we compared, maybe you should be looking ahead and seeing if you can find two of the bars that are significantly different. So let's take a look let's compare E to B. Notice that we have really good confidence in our bars. The error bars are very small, so we're very confident that the mean is somewhere in this area. We're also confident that the mean is somewhere in this area. If you draw the lines across the bottom line for one and the top line for the other, they don't overlap. The two don't overlap with each other. Let me make that clear again from the other one. Look at this one. This one, they overlap with each other. They bump into each other. I can draw them so they bump into each other. I cannot draw this one in any way so that it will bump into, so B and E never bump into each other. So that means we have something statistically significant. That means that there is a significant difference between bar B and bar E. Now, is it possible for your lab that you will have some statistically significant differences? It absolutely is possible. What it means is that one of the things that your reader had to read was a lot harder for them than one of the others was. And so then you're going to have a skew and you'll know that it's statistically significant. Okay, that's a long introduction to statistics. There are entire courses. There's an entire AP stats course at the high school that you should all take. And I only have a few minutes to talk talk you through this. My next video, I will show you how to do the calculations. If you're somebody who's a whiz at math, you've done standard deviation, standard error, you feel like you know what you're doing, you don't even need to watch that video. But for those of you that are a little bit less certain of yourselves, watch it, pause, do some on your own, come back, watch my video some more if you need some help. Okay, that's it, everybody. Hope you have a great rest of your day. I forget how to turn this off. How do I turn off my video? I'll just hit stop, see what happens. Why is it not working? How do I turn my video off? I think that now I've got it. I'm so cool.